I'll be talking about deep learning. I will also be talking about approximate inference as a little surprise. But I think a lot of the stuff that I'm going to be talking about today, many of you will have heard of before, but I think the whole story is perhaps what's most of interest here. It's how I see deep learning fitting into what we thought of machine learning in the past and maybe what we think of it going into the future. If at any point you have questions, just ask. I think it's more fun when we take questions as we go. And then just before I start, I'm going to ask a question myself, which is how many people here have trained a neural network themselves? Okay, so that's about half. And how many people here do computer science? Who doesn't do computer science? Let me ask another question. Okay, that's good. Okay. So let's just start. I'll skip this part. So I'm going to start with the very basics. Okay, this is how I see the whole story. So we start off with algorithms. And algorithms are the bread and butter of computer science. We have these programmable computers. They take in inputs, maybe a bunch of numbers that are not sorted. And what we want them to do is produce outputs that are useful to us. For example, we might want to sort those numbers. And what we do as computer scientists is we write algorithms that perform this task. They take unsorted inputs and produce sorted outputs. And the job of a computer scientist is to design these algorithms and to analyze them, to understand what their properties are and when they work and when they don't work, how fast they work, and so on. Now, there are certain tasks that we deeply care about for which we don't really know what the algorithm should be. For example, if we want to take an image as input and produce a label that says this image contains a horse, what people call image classification, for a long time we didn't know what the algorithm that could do this task was. And this is where AI and machine learning comes, in my view. It's about designing methods that figure out the algorithm by themselves, whether it's through data or through experiences that the computer has itself. Now, this isn't an exaggeration. When I started my PhD, I really didn't think we would solve this problem in my lifetime, the classification problem. So it's really exciting to see that this is almost considered to be a solved problem now. And I'll talk a little bit about how that came to be. But before I do, I want to make an analogy. And the analogy is to point out some of the confusion that arises when people talk about AI. I think there's two axes that are important to think about. One is how useful a certain technology is right now, and another is how general a technology is going into the future. So if you think about flight, let's think about flight first. We had people who would stick wings to themselves in the early days, and it was neither useful nor general. It's not what we use now to do flight. But we also had ladders, right? Ladders were very useful. They kind of got us off the ground a little bit, but only so far, and they didn't really take us all the way where we wanted to go. And then when people came around and thought about the theory and really thought about the fundamentals of physics and aerodynamics and so on, what that led us to was the rocket ship moment, right? When we really nailed it and then it just wasn't a problem anymore. And I think that's what people are searching for in AI. We have these little chess tournaments and all sorts of other tournaments that people get excited about. And in my view, they're not very generally applicable. I mean, these computers can only play chess or Go or whatever. And other than playing those games, they're not useful for other things like scientific discovery or medicine or finance. We have robotics that actually do stuff in the real world, but they don't do everything that we want them to do. And we have some theories about consciousness, which are consciousness and thought and planning that are super general but not very useful. And the billion-dollar question is right up in the corner, right? How can we find a system of tackling this learning problem such that it works everywhere and it works for things that we care about? And the whole story that I'm going to tell today is one particular view on how we might achieve that goal. So let's start off with deep supervised learning. Prior to about 2012, the way people looked at this particular problem of image classification was to write algorithms that looked like pipelines. So you would start off by pre-processing the image a little bit. You would maybe smooth out the colors or do some sort of whitening. You would extract some features that you thought would be useful for the classification task. Maybe you would find corners or edges. You would compute aggregate colors. You would compute texture features. You would prune out some of these features possibly. Then you had a learned discriminator that you would put on top of the features. And then maybe you would do some calibration afterwards. And you had PhD students effectively working on each one parts of this pipeline in separation. So you would have someone who was a feature extraction expert, another one who was a learning expert, another one who was a calibration expert. What deep learning came and did, the simplest way of describing it in my view, is that it said all of these boxes we have to learn simultaneously. So it said I'm not going to try to design the features myself. I'm not going to try to select them myself. I'm going to put all of this into one embedded learning system made up of very, very simple rules. I'm going to learn the whole thing end to end. And that's deep learning, in my view. In practice, how people approach the image classification problem was with something called convolutional neural networks. So these are neural networks that have a particular connectivity structure, which is that the image is processed by a filter that is convolved with the image at multiple locations. And this produces the feature maps that you see here. And for every filter, you have one feature map. And then you optionally do some pooling, you add some nonlinearities, and then you repeat. So you have other filters going over the feature maps. You have more pooling, more nonlinearities, and you repeat this multiple times. And what the learning system is doing is adjusting the parameters of the filters such that when you give it some input data, it produces the right outputs. And the way it does that is through a mechanism called backpropagation. So I'm not going to go into the details for this. There are lots of really good tutorials on that. But this is basically how it works. And this picture is slightly misleading because the networks that people use in practice these days are much, much deeper than this. So the amount of work being done by a single filter is actually a very small unit of work. But the whole thing in aggregate does something remarkable. It classifies images. For example, this is from the paper that kind of really started everything off, Alex Krzyzewski and others. These are some example images that we can correctly classify now. In some cases, I certainly wouldn't be able to classify this image. I think it actually gets it wrong here. It says squirrel monkey, but the label is Madagascar cat. But the leopards, what's the difference between a leopard, a jaguar? I don't know. A cheetah, I think I would be able to tell. But the crucial thing is, at no point did anyone actually come and say, eyes are what are important or spots are what are important for this classification task. It was just learned. And to put things into perspective, I really like this chart. This for me summarizes the whole deep learning movement. The dots on the y-axis are the performance of the different methods that were submitted to this ImageNet challenge, which is an image classification challenge for different years. And 2012, first of all, you'll see that they always had something around 25% error, so lower is better. 2012, these were the methods that were using traditional computer vision, so no deep learning. And the Krzyzewski method that I just mentioned came in and it effectively halved the error rate. And it was using a technique that people at that time thought was hopeless. So they didn't think it was elegant or it could work in practice. So that was really exciting. What was more exciting is that 2013, everybody had switched. So within a year, everybody was doing deep learning. And the slope of the curve also increased. So we had this plateau, and then people started improving on this task again and again. And 2016, I think we're under 3% error, which is better than a human can do this task. So the ethos for deep learning is to think very clearly about the loss that we care about. So the loss is the metric for the system's ability to do the task. And you optimize everything directly for that loss. You don't try to come up with a loss yourself that you think is correlated. You do it direct. You do training end to end, so you don't think of it as a pipeline, you think of it as one big aggregate system. You try not to engineer anything. But when you try to not engineer anything, you end up having many parameters. And to learn all of these parameters and not to overfit, you require huge data sets. And to process these huge data sets, you need lots of computers. So it's big data, big compute, and minimal engineering. I would say that's how you could summarize deep learning. And one of the exciting things that people have found is that, for example, if you train with the objective of classification, the kinds of networks you learn end up being useful for lots and lots of other tasks. So they end up being useful for segmentation, detection, place classification, localization, lots of other stuff. So understanding how these things work has also become a field in and of itself. And clearly, it's not just image classification. So similar techniques have been used to classify text, whether from tokens, noun tokens or word tokens, or directly from characters. There are people working on video classification where the input isn't an image, but it's a video, and you're trying to detect what kind of action the person in the video is taking. And despite the fact that the ideas in deep learning are actually very old, they're starting from the 60s, 70s, there's constant innovation in how people actually wire up these networks. So I'm glossing over the exact details of the convolutions and so on. But in the past year or two, there have been lots of interesting ideas like inception and residual connections, batch norm. Each one of them is worth looking at in detail, which means that this business of taking an input and mapping it to an output is getting easier and easier to do. So this figure that I'm showing down here is a state-of-the-art ImageNet classification network from last year, where each one of the boxes is a layer. So figuring out exactly how you connect the layers and how many you put is what many people spend their lives doing, to give you a sense of scale. Okay, but for those of you who've done machine learning isn't only about supervised learning. There's lots of other things that we want to do. We want to do modeling of sequences like in text or speech or audio. We want to do unsupervised learning, self-supervised learning, generative modeling, probabilistic modeling in the sense that we want to assign probabilities to events that are going to happen or haven't happened. And what's happening is the techniques that were used in classification, in my view, are permeating through all of these different areas. So many people who consider themselves to be generative modelers, myself included, now are beginning to use deep learning methods to improve what they were able to do. And I'll give you some examples of how that's possible. But one really important question when you actually start thinking about deep learning in practice is, where does the data come from? So to learn that classification task, people train on 1 million images of, and so these are high resolution images that humans have gone through and annotated. This one contains a leopard, this one contains a cheetah, and so on. And if we think about that general solution to AI where we have one algorithm that solves all of our problems, it's quite unlikely that we'll have to, or we'll be able to spend that much effort collecting annotated data sets for every task. And even if that were possible, even if we had the resources, there would be privacy concerns and so on. Like if I want a robot that lives in my house, I wouldn't want my house to be in a public data set, right? So how do we solve that problem? Where does the data come from? And there are many people who think that the solution to this is reinforcement learning. So this is where the agent, through its interactions with the world, creates the data that it uses to learn about the world. And that's effectively what reinforcement learning is about. So we have agents, they act, they need to interpret the observations that they get in response from their actions. And from that, they learn to do interesting things. So this is a pictorial depiction of this. We have the agent, like I said, there's an environment, Actions are things like I pick something up, I move in a direction, I say something, and the environment responds either by changing the agent state. If you pick something up, maybe you move slower, or by changing its own state. If you pick something up, the object doesn't exist in the world anymore. And it also gives back rewards to the agent. So it says, now that you've eaten this object, you are happier or you have more energy. And the agent's job is to look at these actions and observations and to formulate a plan that maximizes its reward. So the assumption is that all the agent is trying to do is to make itself happier in the world, and in that process it's going to learn about cheetahs and leopards and all of that stuff. Any questions up to here? No. Okay. Not necessarily. So there are some reinforcement learning algorithms that are based on dynamic programming, but it doesn't have to be. So we'll talk about some algorithms in a second. Yeah.
And this measure of happiness, what is that for the agent, and how do you make sure that it just doesn't become selfish?
So the agent is selfish with regards to happiness, at least how people normally formulate it. And it's assumed that the happiness of the agent is specified by something that is sitting outside both the agent and the environment, effectively. So that is us, the machine learning designers. And the hope is that we design the whole system in a way that ensures that the agent's happiness is aligned with ours, right? And there are people who take that single problem very seriously and think about how you can ensure that alignment happens, and how you can test for bugs in that alignment. I'm not an expert in that, but people do think about it quite seriously. Okay, let's continue. So reinforcement learning, like deep learning, has been around for a long time. It's not a new concept. Back in 1989, people were using RL for backgammon, to learn how to do backgammon. And more recently, people started using kind of neural network-based approaches to control a little car on the circuit in the top right. And more recently, people are starting to do robotics in simulation and in the real world with reinforcement learning techniques. What I'll do is, from here on, I'm just going to be talking about different papers that touch on some of the things that we've talked about. The first one is going to be a paper that came out of DeepMind in 2015, which many of you probably have heard about. This is the DQN algorithm, and it was the first, arguably it was the first convincing application of deep learning techniques to the reinforcement learning world. And that's why it made such a big splash. What people did was they started looking at Atari games. So this is a console back from the 80s or 70s, I think. And Atari games were games that were designed for humans, obviously. You have a screen that gives you some observations of the game state, and you have a controller through which you take actions to play the game, and the reward is well defined. It's how many points you have in that game. And humans enjoy these games because we find them to be at the right level of difficulty, so they're not too easy and they're not too hard. And people thought that if we get a computer that can learn how to play a wide variety of games, that would be one small step towards having an AI that could solve a wide variety of tasks in the real world. And what's really key here is that the games were not designed for AI research. They were games that existed in the real world anyway. And so there wasn't any worry about the games having been simplified or adjusted to make the algorithm shine. So there was no cheating allowed, effectively. So, like I said, what the agent is trying to do is trying to maximize its rewards. And the way people start thinking about this mathematically is they say that if I'm at time t, I'm going to label every reward that I get from t into the future by r. So rt plus 1 is the reward at time t plus 1, and so on. And if I sum all of them up with this extra gamma factor, which says how much I prefer the current time in comparison to times in the future, then I will get a sense of how much reward I expect to get from my current position all the way into the future. And that is the quantity that the agent is trying to maximize. Okay? So this balances kind of long-term thinking with short-term thinking. And one of the ways in which people get a grasp on this is by defining this mathematical object called the Q function. So the Q function is something that looks like this. It's a function of two variables, the state and the action. The state is just a description of the state of the world and the state of the agent. And the action is the action that the agent could take. Okay, it's not the action that it does take, but the action that it could take. And what this function returns is an expectation of the reward it would get if the agent was in state S and it took action A and it was following policy pi. Okay, so think of this object for a second. And then if you had this object, what you could do, one algorithm that you could write is to say that I would design an agent that would take the greedy action all the time. So whenever it observes itself in state S, it would put S into the Q function, and it would search over all actions A, and it would pick the action that gave it the maximal reward. And that would be the greedy agent. In practice, though, as many of you know, being greedy all the time doesn't work, and a little bit of exploration is useful. So one classic way of doing this, very naive but works relatively well in practice, is epsilon greedy, where with some probability you take the greedy action, just like I described, and with the remainder probability you just explore randomly. And by adjusting epsilon, you can learn about the world because you're taking random actions, and also exploit the world, which is taking the action that gives you the maximal Q value. Now, obviously, to have agents that actually do interesting things in the world, we need to learn this Q function. That's the whole point. So, to start off by doing this, we can think of what would be the best Q function that we could think of, right? And people call that Q star. So Q star is a particular Q function that corresponds to the policy that would give you the maximum expected rewards into the future. So it's doing a search over policies. It's saying how should the agent act in the world such that in any state it's likely to get the best rewards. And if you do a little bit of math, this object ends up looking like this line, which is the expectation of the reward that it would get in the first time step, followed by effectively the best reward it could get if it took the best action. Okay. So this hasn't done much. It's saying Q star is equal to an expectation of something that involves Q star. We haven't solved the problem yet. What people do is we say, okay, I don't have access to Q star, but I can imagine starting with a Q function that is not the star Q function, but is parameterized by a bunch of parameters theta. And what I'm going to do is learn theta to make my Q more similar to Q star. And this is where deep learning comes. This innocent-looking function, they parameterize as a massive deep network, and then they optimize theta. Okay. Yeah, so that's pretty much it. So like I said, the deep network, what it does is it takes an image of the game state, for example, breakout. It takes an image of the game state as input, and it applies the same tricks that we talked about for classification. So convolutions, pooling, nonlinearities, followed by more convolutions and pooling. And what it outputs are a bunch of numbers for every possible action. Okay, so this is an implementation of the policy, effectively, or the value function. It depends which algorithm you're talking about. Now, to optimize that network that we just drew, we look at this equation again. This is the equation that we had talked about in the previous slide. And basically it's saying that in order to make this equality hold, so what we can change is Q. That's what we're allowed to change. And what we want to do is to ensure that this equation holds. What we do is we define the target, which is effectively the right-hand side of the equation, and our current value, which is the left-hand side of the equation. It's over here. And we take the difference of these two guys, and we want the squares of this quantity to be as small as possible. So it says, I want my left-hand side to be similar to my right-hand side, and that's the optimization objective. And then once you have this loss function, you can differentiate it with respect to theta, which is this object here, which gives you gradients, which are effectively descriptions of how you can change your parameters to optimize the loss. And you take a step in that direction, in the direction specified by your gradients. So it completely falls into the normal deep learning gradient-based approach. Okay. Any questions up until this point? Yeah.
Yeah, so you were saying that wanted to make a system without kind of any engineering tasks involved, but
Yeah.
so I guess is that's not necessarily.
Yeah, so when you're doing research in this area, you're always trying to strike a balance between engineering something that makes the systems work better and engineering something that works in a general way. What people have found is that convnets, even though they are heavily engineered, they're useful all over the place. Like anytime you're doing anything with an image, basically, a convnet is useful. And one way of thinking about it is that the convnet is building in this knowledge that we know about images, which is that they are largely spatially invariant, which is that if I see a dog in the top right of an image, it doesn't matter if it's there or if it's in the bottom left of an image. And that's the knowledge that it's building in. So you're right, there is a huge amount of engineering in there, but people just find it so useful that they're happy to live with it.
How do you get the function with theta close to the function you want to be? How can you really get a good approximation there?
So the loss is defining goodness of the approximation. And you're right that the space is really hard and that there's no reason that if you were to take these small steps, you would get to the global optimum. In practice, people find that if you allow the space to be large enough, there will be many local minimums that are as good as each other. And the question you just asked is one of the reasons why people were so skeptical of neural network methods a decade ago. As far as I'm aware, there are no theoretical guarantees that they do anything useful, but in practice, they seem to work really well. Yeah.
So for a normal image classification CNN, and you say no, that's wrong. So when you
So there's a whole zoo of algorithms, and they do everything that you can imagine. There's some that wait, there's some that don't wait, and to be honest, I'm not an expert in RL, so I don't know which ones are more heavily used than other ones. But we'll talk about another one, which after this, which is asynchronous, which slightly changes the way you do it. But this issue actually comes up in exactly this slide, which is in practice, this objective, this loss function that we've written is slightly tricky to maximize when theta is constantly changing. So every step you're changing the loss function itself, and that makes things very unstable. And so one of the tricks that got DQN to work in the original paper was that they would fix this theta, the parameters of this left-hand side for several thousand iterations while updating the theta on the right. And one way of thinking about this is is, maybe I'm overblowing things here, but you can think of it as an agent that plays a game for a day, and then it compares itself to what it was like yesterday, and it learns overnight, right? And it's not constantly comparing itself to itself right now. It's comparing itself to what it was like a few days ago. And this, people find, is very stabilizing. Yeah?
So the Q function is often discontinuous if you look at it as a function of the state, or the action doesn't really matter. So
yeah, you basically ignore it. So the discontinuity with regards to actions, people get around by formulating it as it takes an image in and it outputs actions effectively. Discontinuity with regards to images, people just ignore. Yeah. So to summarize, if you were to actually implement this, you would start off with the agent that takes actions and observes things, like I said before. This agent would actually store its experiences in a big database, and you would sample these experiences in a learner, and the learner would kind of talk to a parameter server, which is kind of holding the current state of the agent's brain. It would ask for the parameters, it would look at its experiences and figure out what the gradients should be. It would send the gradients to the parameter server. The server would send it to the agent, and this would continue. And so you would design this loop, you would let it run for a very long time, and then you would get an agent that does interesting things. For example, I'm just going to go through some examples quickly. This is Space Invaders. Before training, the agent is effectively taking random actions. So it's doing epsilon greedy, but even the greedy action is effectively random. So it's not getting anywhere. After training, it's a completely different story. It basically plays as well as the best humans do. And it learns interesting concepts, if you will, that people didn't expect the system to be able to learn. So there's this purple spaceship at the top that comes around and it gets hit with a perfect shot. And the agent learns to do this because the spaceship gives you like 300 points, whereas the other guys give you 10 points. So by looking at the problem at that super abstract level that I was just talking about, you get this seemingly complex behavior out. Another nice example is Breakout. So after a while of training, so at the beginning it can't even catch the ball very well. It doesn't know that it's good to catch the ball. But after a while, it gets this concept quite nicely. I think by this point it's completely nailed it. And then it starts doing something that humans can't reliably do, as far as I'm aware, which is that it starts putting the ball behind the blocks. So it kind of digs a little hole on one of the sides, and then it sends it back, right? So this is really exciting, right? I mean, you start off with a few equations and then you get this behavior out, and the behavior is encapsulated in this deep network, and you think to yourself, oh, wow, okay, what's going on here? Is there something bigger happening? Just going to ignore this for the sake of time. Yeah?
So each frame is the input of the system.
Yeah, so they actually concatenate 4 frames to each other. So you can think of it as 4 frames stuck to each other as being the input. And the reason they pass 4 is because the agent needs to have some way of estimating speed and direction of motion. So that's a little simple trick that you can do. But in the next paper, they don't do this. They have a different way of getting speed out, which I'll talk about in a second. So then if you look at all the games in this Atari suite, the computer learns them to a fairly high degree, and for many of the games, it learns them better than a human could do as well. So we have one expert player whose job is to play games, and we compare the agents against that guy, and often he loses. But the good news is that there are actually quite a few games that humans are much better at, and the agents completely sucks at. One is famously Montezuma's Revenge, and this is a game that involves very high-level planning. Like you have to pick up a key in one room, take it to another room to get another key, and take this key to a third room and to progress. And effectively, the agent never manages to do that sequence of actions in order to get any reward to learn anything at all. So it's completely just dead. And so that's an example of an open research question, and the solution to that, I think, is going to be quite complex. But the whole reason why we wanted to do RL was because we thought that data was hard to gather, right? And one could argue that we've almost created another problem for ourselves, which is that these agents require enormous amounts of interaction with the world to learn anything. So these are the learning curves for, I think, four of the games in the Atari set. And they're training for 200 epochs, and they're still learning at 200 epochs. Each epoch is about 50,000 interactions with the environment. And this takes about 30 minutes of real-time compute. So each one of these agents is taking about 5 days to learn from scratch on fairly beefy computers. And first of all, this is quite slow. Humans certainly don't need 10 million interactions with the game to learn the game. But also it limits the places where we can use reinforcement learning. Like if we want to have, well, I won't make that example. Like if we want to have RL agents in the real world, we might not be able to afford that kind of interaction. For example, this is effectively the same algorithm that I just described. Where the robot is learning to put items in, like put pegs into those holes, I think. This is what it looks like as it trains. So obviously many people have started looking at improving the algorithms that we use to train these agents. And this can start from the reinforcement learning loop itself. This is a paper from our group that came out earlier this year. And this is called Async RL now. And what they wanted to do is to speed up DQN to allow for the agents to learn so-called off policy, which means that they can look at another agent taking actions and still learn from their experiences, and also to be able to handle discrete and continuous action spaces. So effectively what happens in this model is it's a slight tweak, which is that you have one shared brain, effectively, and you have k parallel actors. So these are, imagine k separate computers that interact with one main computer that stores the brain. These computers take actions in the world, they observe rewards, they compute their own gradients, and they send their suggestions back to the brain. And the brain decides how much to take into account from each thread. So it's a very similar situation to what we had before. We have this target object, and we're trying to get y, the target, to match our current q value. We compute the gradients with regards to the parameters, and we update. A slight modification that they consider, this is like getting into RL technicalities, but just to give you a flavor, the targets that we talked about in the previous work, they were always what people call one-step targets, which is that you take one action, you observe a reward, and from then on into the future, you assume that you're following the estimates produced by your Q value, by your Q function. But another way of doing it is by taking n actions, observing the rewards that you get at all of those n actions, and then after n plus 1, you use your estimate, the Q function. And by playing around with n, you can play around with how much it relies on its estimations versus how much it relies on its experiences. So when you have an n-step function, what's happening is you get rewards from t to t plus n, and then from there on you're going to say, I'm going to assume I follow q. That gives you a new y, and you follow the same gradients. In this work, they also kind of slightly changed the setup of the network. So instead of it just being a convnet that takes 4 frames as input and produces actions out, it's actually a recurrent net. So one input is the image. This gives you a hidden representation that produces the policy and the Q function. Then at the next time step, you get a new image. The hidden representation is now a function of your current observation, but also the state you had in the previous observation. And for example, this allows you to compute velocities, how much something has moved over time. Just skimming over results here, this is just showing that for a bunch of different games, Beam Rider, Breakout, and so on, as you increase the number of threads, so going from blue to yellow, you effectively learn faster. And this is a good thing, right? It shows that if we have a tough problem that requires a lot of experience to learn, we can solve it by having many learners work in parallel. So that's basically it. And lots of benchmarks. We started off with DQN that was taking in the order of a week on a GPU to train. And this method that I just described takes about half the time on CPUs, which are much more abundant, and gets much better performance as well. So this is just a flavor of the kind of improvements you can make to the RL algorithm itself. But when you do make the algorithm stronger, what it allows you to do is to work in more interesting environments. Yeah.
Is it hard to do that one for GPU, or could it still be sped up?
I don't think it's hard. So there's when it comes to CPUs, GPUs, and RL, there's the requirements of the math. Like sometimes you're not allowed to do an update until you have certain experiences or not. But there's also the practical nature, which is whether it's faster or not to do it on GPU or CPU. I wasn't personally involved in this work, so I don't know exactly why they switched to CPUs. But I imagine it's a combination of those two concerns. So you're often limited by the mathematics of what you're allowed to do, but also by just how much time it takes to send parameters over the network and so on. So a series of environments that people are starting to look at quite a lot in DeepMind are these labyrinth environments, we're calling them, which are 3D environments that allow us to specify tasks that we think are going to be useful in prototyping of new algorithms and new agents. So in this example, the agent, what it's trying to do is to navigate a previously unseen maze and to find all the apples. The apples give the agent reward, and they make them happy. And in the process of this, what the agent is effectively learning are things like navigation, attachment of reward to certain concepts in the world, i.e. apples, and there are a myriad of variants. Like sometimes you have to go back to where you started from to get your reward. Sometimes some things hurt you, sometimes some things help you. And as we make these agents stronger and stronger, we can make the environments and tasks more and more similar to what we would care about ourselves. Okay. This is a nice time to ask questions if anyone has one. Yeah.
You may not know the answer, but with regards to the speed up of A3C, is that...
Is that a thread per what core?
For all of the threads in the A3C method, do you know if they were running on actual physics?
I don't know. Yeah. Yep.
When it comes to the actual reward, that
So the agent has a separate stream of information that is just the reward. So it has two streams coming in. One are the states of the screen, so it's the visual stream, and then it has the reward stream. So in that sense, it knows the reward is something special because it's separate. Now, it knows that it has to maximize the reward because that's what we build into the equations, effectively. It has no other, it can't choose to do anything else. It has to do that. But one alternative you could consider is the situation where the reward is inside the visual stream, right? So these games, they often show on the screen how many points you have. And you could consider an agent that has to actually look at the screen to figure out how much reward it has and then try to maximize that. That's not what people do typically because they think that it just complicates the problem with no real benefit. But that's something that you could consider as well. Yeah.
Has there been any research into having a single network try and learn?
Yeah, so that's what you really want the agent to do. There's been a ton of research on that. In general, it's very hard to do. For example, a bunch of people from DeepMind, I think maybe a couple of weeks ago, 2 or 3 weeks ago, published a paper called Progressive Nets. And it falls into this kind of framework of continual learning or continuous learning, incremental learning. And in general, I think it's a difficult problem. People don't know how to do it. You can always make the network so big that it learns each one of the tasks separately, but figuring out a way to get it to actually share concepts from one game to make it better at another game, that's still very hard. And actually, this is something that I'll be talking about a little bit now. Yeah. Okay. Yes?
So you're creating frameworks and models.
So that's a really good question. I should have mentioned this. So in all of the experiments that I've showed so far, it's one code base, one agent, one architecture that is playing all of the games. The game that we're playing as researchers is that we're not allowed to fine-tune our systems for a particular game. And because of this, we hope that we end up with algorithms that are general. Okay. So do you think we should take a break now? And yeah, I think there's a 10-minute break, and then we can come back for the rest. Thank you. All right, okay. So for the rest of the talk, I'm going to shift gears a little bit, and this is going to be more about the kinds of stuff that I work on myself. And it broadly falls into the category of model-based methods. So what we've done is we've looked at supervised learning, where we take in interesting inputs, we learn these kind of internal representations, which I call Z, that are somehow useful for a prediction task of interest. So X goes to Z, goes to Y. And a very simplistic depiction of what happens in reinforcement learning is what you see on the right, where you have frames as inputs, you form a representation, and what you produce as output is an action. And the RL algorithm, all it's doing is providing the data from which you learn this big network. And as we saw, for problems of interest, you still require a ton of data to learn this network. So this is how I see generative modeling fitting into this picture. We still have these images as input, these X's, and we still care about learning a representation Z that is useful for some downstream task. Maybe it's classification or it's taking an action. But what we're going to do is we're going to build a model, what you're seeing on the right. And this model is capable of turning Z back into X. And what the model does is it's a specification of our prior knowledge, perhaps, of what the world looks like, right? So it says how abstract concepts manifest themselves in terms of visual or sensory observations. So to make this clear, I'm going to work on this example. Imagine you were designing a system that took images of eyes as input, and it was trying to classify whether the eye was blinking or not. And the intermediate representation Z might be, where the center of the eye is and how open or closed the eyelid is. Now, if we had access to a model that took any particular configuration of Z and produced a synthetic image of an eye, then what we could do is we could leverage that to learn the mapping from X to Z. So if I have very few labels of images and associated blinking or not classes, I could use this model to bootstrap my learning. Okay, so this is a really fundamental part of the talk. If it's unclear, speak now. Okay, that's good. So really, model-based learning, in my view, is all about two things. It's about learning the representation Z. It's not about generating images. It's about learning Z, and it's about data efficiency. So I'm going to start with some work that I did during my PhD, 2011. This was before ImageNet happened. So if we had 2 layers, that was considered deep back then. We worked in this model that was a model of images. And what it's trying to do is to learn a probability distribution over images. So this is saying what X's are likely. And the way we did this was by using a structure that people call deep Boltzmann machines. And the way this works is that in 1D, if you represent your image as a vector, it would model this with several layers of latent variables. And the particular connectivity of these latent variables to the visible vectors were what made the work special. We call this a shape Boltzmann machine. And you can think of it as a convolutional deep Boltzmann machine. So we built into this model knowledge that we had of images like people do in ConvNets. And this allowed us to train on small amounts of data. This is the view in 1D. In 2D, you effectively have a set of latent variables modeling every little patch in the image. And you have one set of latent variables modeling these guys. So the idea is to explain any image, I'm going to form these abstract concepts, and these concepts are going to be useful for downstream tasks. Now, clearly an important thing you might want to do is inference. And inference is finding likely values of the hidden variables given an observation. Or, for example, inference could be producing plausible observations from scratch. So back then what we were doing is using Markov chain Monte Carlo techniques for inference, where specifically Gibbs sampling, block Gibbs sampling, where you would start from a single image and this would give you the vector V. You would sample a likely H1 given V. You would sample H2 given H1. And then given this new value of H2 and V, you would sample H1 again, and you would keep doing this on and on. And if you do this for long enough, what you observe is a sequence of images at the bottom, which the model effectively thinks are likely images under the model. So this is one way of inspecting the quality of the model that you've trained. So let me show this video. So in this video, it's an interface that allows me to play around with this model that I've trained. And the model was trained on horses, black and white images of horses, and I'll explain why in a second. And what I've done here is I've cut out a piece of the model, a piece of the image. So what it sees are these black and white pixels in the surrounding, and what it does not see is this part in the center. And with MCMC sampling, like I just described, we can ask the model to fill that in. So what we're saying is, what are likely explanations for the piece in the center? And every sample is going to be one plausible answer that the network produces. So it produces this, and this is nice because the shape of the horse looks plausible. It matches up with the observations. And as I cut out more and more of the image, the variability increases. So it has a notion of the variability inherent in the data. And when I cut out more, the position of the head goes up and down. The legs, sometimes you can see one leg, sometimes you can see two legs. And the key point here is that this is all learned as well. At no point have I said anything about horses specifically to the model. So what I did there is I drew a couple of black pixels. So this is an additional constraint I've imposed. And now I'm going to ask the model to explain to me how it thinks that image can be completed. And what it does is it brings the horses back down, right? And again, it's just learned this from data. And I can draw a little leg there and see what it does. And it brings it up, right? So this was kind of demonstrating to people back then that, learning works and you can do interesting things with it. But the most important part is that you can take the same model exactly, apply it to a different data set of, say, motorbikes, and then what you have is a strong model of motorbike shapes. And you can do the same kinds of experiments there. Put a white blob there, and it changes the type of the bike. It becomes more racy, and so on. I'm going to skip over the rest of this. So the component that I just described is this component that says, given a bunch of hidden variables that are discrete abstract variables, what are likely shapes? Is this a likely contour for a car or not? And then what you can do, for example, is you can combine this knowledge of shape with knowledge of colors and construct a model that looks like this, that says, to explain an observation X, I have some shapes and I have some colors, and they combine to produce X. So this is the knowledge that I'm building into the system. That's the model in the right-hand side in the figure a few slides ago. And then what I hope is that given X, an observation, I can recover the appearances and shapes, and this is going to be useful for some downstream task. And this is what we were able to show, that after having trained this Boltzmann machine and associated color network, given these inputs, we were able to get these outputs out. So it's using its knowledge about what humans look like to produce a very decent answer for the contour of a human body given an input. Now, the way people solve this today is actually with deep learning. So you just have a CombNet, you train it on many, many examples of images and part annotations, and it does way better than this method. But this was at a time where the data sets weren't available and we were trying to bootstrap. So this is one example of how model-based learning can help you when data isn't as freely available. Same method applied to a different data set gives you comparable results. Now, inference in these models was done with MCMC, and MCMC is very slow and hard to mix. And naturally, deep learning has an answer for inference as well now. So what people do nowadays, or some people do nowadays, is they start off with this structure over here, and basically this quantity P of Z given X, this is the probability of the latent representation given an input, and your model. This is going to be too hard to compute. We're going to assume that we can't run MCMC for long enough to get good answers. So we approximate it with another function called Q. So Q, we're trying to match to P as well as we can. And this Q function we're going to parameterize as a deep neural network. So we parameterize Q by a deep neural network. This is giving us the mapping from X to Z. Optionally, we're going to parameterize even the model by a deep neural network. So this is the mapping from Z to X. And we're going to try to make Q of Z given X as similar to P of Z given X as possible. And we do that by minimizing the KL divergence between these two distributions. And the KL divergence is just a measure of how similar two distributions are. And you can do this with gradient descent, which is very deep learning compatible. So you can learn both Q and P at the same time. So you learn the inference network and the generative model at the same time. So to draw this a bit more clearly, what you could do is you could start with an image, just express this as a neural network that gives you Z, and then another neural network that from Z produces a reconstruction of X. And this is what people call autoencoding. It's a very classic way of producing codes Z that are low dimensional and representative of X. So this network, as I said before, is the inference network, and this network is the generative model. In the variational framework, this idea is called the variational autoencoder idea, and it's absolutely everywhere. So if someone talks about deep learning in the context of generative modeling, it's quite likely that they're using a structure similar to this. Now, a cool paper that came out in 2015, this reference is wrong, is a paper called Draw, and they take this idea to the next level. So they observe that actually sometimes it's useful to produce this latent variable Z over a sequence of computations. So sometimes it's going to be hard to look at an input and immediately know the best way of describing that input. What happens is X is read once to produce the first estimate of Z, and this estimate of Z is going to be used to compute the first attempt at the reconstruction of X. So T is the first attempt at reconstructing X. And we have these recurrent networks, and what they do is they look at X again to produce an updated Z, which is going to additively write to this C variable to produce CT plus 1. These C's in this paper, they call them canvases. So the canvas is effectively a canvas that the model is drawing to in its attempt to reconstruct X. And it can look at the image multiple times, and it can draw on the canvas multiple times to do this. Additionally, what they do is they make each one of these read operators attentive, which means that the network doesn't look at the whole image at the same time, but it looks at small patches at every step. And they also make the write operations attentive as well. So you write to the canvas only one small patch at a time. If you train this whole beast, which is also just a deep network, I've drawn it in this way, but if you put this as the output and this as the input, it's just another deep network. You get a system that produces samples like this. So the final output of the network is this final column is drawing MNIST digits. But in order to produce each one of the digits, it's going through, say, 12 or 16 steps. And its attention at every step is visualized by these red squares. So what it's doing is it's learned that in order to draw a 3, it starts off at the bottom and it moves slightly to the top and finishes off the 3. And this is really exciting because it looks as if it's learned the underlying cause for that image by itself. It looks like it's understood that there's a brush that moves over the image in order to produce the signal that it's observing. Not only that, but it also produced state-of-the-art samples of MNIST digits at its time and for a bunch of other data sets. So this is an example of the same system drawing these street view house number digits. And here the semantics are slightly different, so it doesn't really draw like a pen as it does for MNIST, but still it produces very sharp images that were state-of-the-art at their time, and points to yet another way of structuring these networks in order to get behavior that is more data efficient.
What sort of,
Yep.
so in the central layer where it's as encoded as possible, what sort of reduction in the data size you gain?
So people don't, with these models, they don't really measure reduction in data set, so they assume a fixed data set size and they look at how well you can model this data. It's kind of assumed that the data set is too small for you to, you can overfit on it basically, right? So if you can model held out data better, it's assumed that the structure that you're using is better.
Oh, sorry, I mean, so are you getting actual like compression of the image?
Oh yeah. That's definitely happening. I don't know the numbers off the top of my head. There's a recent paper by the same authors this year, and it's called Towards, I think it's called Towards Contextual Compression or something along these lines. It's a very similar model without the attention part. And what they show is that you can actually have a slider that says, okay, I only want to transmit 1 bit for every image, and then it tells you how good the reconstructions would be. I want to transmit 10 bits, it shows you how good the reconstructions would be. And what the model learns appears to be something that's quite conceptual, in the sense that it doesn't just transmit blurry images if you set it to 1 bit. It transmits images that capture the concept, but not the specifics of the object. So, yeah, people can look at this as well in quite a lot of detail. Yeah.
So for the latent representation, basically which
Yeah.
goes across the several steps. So which one does it?
It kind of depends. Some people look at the Zs. I like to think of the Zs as the latent representation, but arguably the states of these RNNs could also be the latent representation. It's a bit like a convnet, right? It's unclear where inside the convnet is the representation. It's kind of everywhere. Mathematically, I think it's cleanest to think of the Zs as the latent representation.
So all of them together?
Yeah, all of them together. So yeah, all of them together give you the final code. So when we looked at that model, we thought that it was tantalizingly close to understanding the underlying scene that generated the data, and we thought if it would be possible to push this a little bit further. I think this is best explained with this figure. If we had a system that could look at this video and understand the objects that constitute that scene, then it would be much easier for the system to learn to take actions in this game that maximize its reward. And surely you don't need rewards to understand what objects are. Surely if you just have a stream of video of this game, you can understand that certain things move together and that they are objects and that they are things that you should model yourself. So this is where we set off. Another way of thinking about it is in the context of graphical models. So graphical models have been in machine learning for a long time, and I think in this particular case they're quite elegant. So the simplest graphical model you can draw, well, not the simplest, almost the simplest, is one with 2 variables. You have z, which is the latent cause, and you have an observation x. And this model, what it's depicting is the assumption that z causes x. So the cause blue brick causes this image that we observe at the bottom. Now, if you only are willing to operate at this level of abstraction, you face a problem, which is that if you observe an image that looks like this, the only way you can represent that image is with a cause that effectively says, okay, I'm looking at a pile of bricks. And it's not going to be specific enough. It's not going to turn each one of the bricks into its own symbol effectively, something that you can discretely manipulate in order to act. However, if you have a model that looks like this, where you have 2 causes, one would hope that after learning, when it looks at this image, it would actually say, okay, there's a blue brick and there's a red brick. Okay? And this would be ideal to have. You could go one step further even and say that every one of these causes isn't just about the identity of the cause, but also the position of the cause in the image. So for example, you could have a what and a where for every object, and you could have multiple objects. So then the explanation you would get is that I have a blue brick and it's situated above, and I have a red brick and it's situated below. And if I could learn this representation at the top unsupervised, without rewards or labels, then I would have almost solved the problem of playing Pac-Man. So the VAE structure that I just talked about is effectively doing inference in graphical models of this form. And we wanted to extend it so that it would be doing inference and graphical models of this form. This gray box I've drawn here is to indicate that actually an immediate problem that you face is that you don't know the number of causes in the world until you look at the image. So the number of causes is itself a latent variable that you have to infer at test time. So if the inference network in a VAE looked like this, where you had one network producing Z given X, and you had another network producing Y given Z, Y being the reconstruction, now we're going to use a recurrent network that takes X, produces the first object's description, and it takes one step, it produces the second object's description. It takes another step and then decides that there are no more objects. And it takes the first two Zs and produces the reconstruction Y. Now, if we could construct this network and if we could learn it, then we would be quite far towards getting object-level descriptions. But that wasn't hard enough, so we added more stuff to it. So now, for every object, it's not just detecting one Z, it's also trying to separate into a what and a where. So to be complete, it looks at X, it decides there's an object present, it's a blue brick, and it's there in the image, and it continues into the second object, and so on. Now, we do use attention, like in the draw paper, and attention here is used both for looking at the image and for explaining the position of an image. So for example, if the image contains two digits, a 4 and a 0, what it does is it first produces this latent description H. H produces the where. So first it says, okay, I think there's a 4 in the top left corner. Once it's produced the where, it actually uses a spatial transformer network. It's a way of kind of cropping an image in a differentiable way to look at the 4 in more detail. Then it tries to model that 4. So it tries to create a code that describes succinctly what that 4 looks like such that it can be reconstructed. And this part of the network is exactly a VAE. Once it's constructed the 4, it uses the where variable that it had inferred previously to paste the reconstruction into Y, and if the object was there, to put it into this reconstructed image. So once you have the original, the 4 and the 0, and you have the new reconstruction 4, this is very easy to compare to so that you know where to look next. So now you know, okay, I need to explain where the 0 comes from. And that kind of moves the recurrent network into the next state. So to summarize, what we are trying to do here is we're trying to build structure into the network so as to get meaning out. We want to make it slightly more interpretable. We want to make it slightly more decipherable, such that the agents or the networks that sit on top of this have an easier job and they can do it with less data. And to do this, we're going to use recurrent inference networks. And this is something that people were rarely doing at the time. And one thing that you'll notice, which is perhaps a little bit unusual in the deep learning world, is that we're actually doing inference over discrete variables here. And the discrete variable being the length of the recurrent network. So in a normal convnet, all the values, all the intermediate values are continuous. So all the feature maps are continuous values that can have, continuous values. But here, you can't say that there are 2.5 objects or 3.5, 3.4 objects, right? It's either 2 or 3 or 4. And the network, in order to learn how to produce these discrete discrete variables, you have to do a little bit more mathematical trickery. I'm not going to talk about it now, but it's kind of something interesting to look at. And for this, we used the reinforce algorithm and it got interesting. Now, the best way to demonstrate what actually happens is with a video again. Again, there's an interface here. And what I'm showing is this is an interface where I can draw stuff. And on the right is a reconstruction of what the network thinks it's seeing in the drawing that I've made. And the boxes indicate where it thinks the objects are. Okay? The colors of the boxes indicate which step they were produced in. So the red box indicates the first time step, and the green box indicates the second time step. So first thing you'll notice is that when I draw the picture on the left, it actually recognizes that there are two things there. There's a 1 and a 2. For me, this is super exciting because normally these, and this is without any labeled information, right? So this is completely off the model. What the network has done is it's realized after having seen many 1s and 2s and 0s and 9s is that those things are things, right? They are separate things that can be modeled separately. So that's kind of cool. I clear the screen, I draw a new one. It recognizes when there's only one object, it recognizes when there are two objects. This part is cool. So I draw a really big 1. At the beginning, it thought that it was 1, 1. But as I extend it even further, it prefers to explain it as two 1s that are kind of just abutting. And the reason for this is because in the training data, it has never seen a digit this big. So the most plausible explanation for it is to say that there's actually two objects that just happen to be aligned with each other.
Sorry.
Yep.
You try the same example with like a number that is not
Like a
number 2. So
A really big
it's
2.
big number 2. Which
Yeah.
is not symmetrical.
It would struggle because the top part of it would know that there are two objects, but the top part of the 2 it wouldn't have seen before. It would try to reconstruct it, but it would just do a really bad job. But it would know that there are two objects. And this one is, again, symmetrical, so it can explain both parts. If I draw a small 8, it knows that it's an 8. But if I draw it bigger, it actually prefers to explain it as two zeros, right? And it's the same kind of idea. This one is interesting as well. So this is a small 8, but the parts aren't connected. So it again prefers to explain it as two zeros. But if they're close enough and small enough, then it becomes an 8. So it's just getting to this notion that what we consider to be an object, for example, in the real world, is actually formed very strongly from huge amounts of prior information that we get. And the prior information is really subtle. Some of this stuff they're not going to be things that you hand code. Like I never expected size to be something that would be important for an object detector, but it turns out that it is. Another nice visualization is of this system learning. So I have a batch of images that is trying to analyze, and what I'm showing in the bottom are its reconstructions of those images over the course of learning. It starts off basically doing nothing. Gradually, it starts getting a blurry notion of what things are where, but as counts are off, towards the end, it knows what objects are and it knows how to count. So gradually, it knows exactly how to explain the data. And it doesn't have to be simple digits. You can have overlapping objects. Same thing happens. This is another data set. It's slightly more complicated than the MNIST digit data, but I think the next slide has a good visualization of this. What I'm showing here is, so if you look at the panel on the right, it sees this image which has 3 dots, and it explains it with 3 steps. It says first dot, second dot, third dot. And when it sees a more complex character, it uses more steps to explain that character. Yeah.
So in the videos you just showed, why do the boxes wobble? Because you said that you do this alternate fair repeat thing until at some point, right, there's nothing else, I'm done. So why do these boxes keep readjusting? Do you just keep running the RNN, or?
They keep readjusting because it's a probabilistic system, right? So every time I give it an input, what it produces is one plausible answer or one plausible explanation for that input. Okay? And if I ask it multiple times, it's going to give me multiple plausible answers. So that explains some of the wobble. That's for the first videos. The second video that was over the course of training, it's wobbling because over the course of training it's giving different answers. So it's...
Oh, right, so the video itself is, it's presenting the same image several times through the training.
Yes, yeah. Yeah.
What is the reconstruction process for this, other than the square error?
It's just the square error. Yeah. Yep.
Does this architecture impose an upper bound on the number of objects you can have?
Mathematically, it doesn't, but in practice, it does. So in practice, because memory is limited in a network, on a machine, we can't allow the computer to entertain the thought of like 1 million digits. So in practice, we say, okay, you're only allowed to go up to 10. But the math works out for an infinite number. Yeah.
Maybe I missed something or I got confused, but you said that it's not that it's unsupervised learning. But where did it see it if it's not supervised learning?
So it's unsupervised in the sense that the data set consists only of images of digits, but at no point do I tell it that this image has 2 digits or the positions of the digits. So all it sees are unlabeled images. And what it's trying to do is it's trying to form explanations for those images that are useful for reconstruction.
So there is still a training set.
There is a training set, yes. Yeah.
Did you try anything other than what and where? Something like
So the what in the current network is effectively capturing style. It's not a discrete label like 0, 1, 2, 3, 4. It's a distributed vector of say 50 numbers that is expressing both the class of the digits but also its style. So the what in this framework is it's entangled style and class. Yep.
why do you use separate representation for the where if you use experimental network?
The separate representation for the where is you could munge the what and the where together, but at some point you have to produce the parameters of the spatial transformer network, right, to feed it into the network, and you could imagine that that's the where. Yeah.
Have you applied this model to sequential data as well?
No, but
Would it
that would be interesting.
To do that? Would it be easy to extend that?
It wouldn't exactly be trivial, but I think it would be interesting to consider. So if we had a video of these digits moving around, then surely that gives you a signal as to where the objects are and what the objects are. I think it would be a very natural next step. So how much time you said? 15 minutes? Okay. Now, this is the most important slide, I think. And this is showing that if you do this generative modeling stuff, you become more data efficient. So imagine the task where we want to compute the sum of these two, like 5 plus 1 is 6, 2 plus 7 is 9. One way of doing this is by training a convnet that looks at images like this and predicts 6, images like this predicts 9. Another way of doing it is by training a network like I showed, the AIR network, getting its explanation for the image and then learning a network on top of that. And that's what I'm showing here. The red curve is how fast the CNN learns this. So it learns to a high degree of accuracy, but it requires, say, 60,000 images to get to that point. The AIR network produces a much steeper learning curve. So with small data sets, it can get very good performance, but its performance plateaus. And this is kind of demonstrating when generative models are useful. They're very useful when data is scarce, but also demonstrates the drawback, which is that they form a representation that might be useful for one task, but not so useful for some other task. And the same story is if you're classifying, for example, if they're in increasing order or not. And an open research question is figuring out how to build generative models that, first of all, don't require so much engineering on our part in terms of an inference network and so on, but still learn compositional structures that are useful for learning downstream tasks faster. And that's effectively what I work on. I'm going to go through this quite quickly. One thing you can do is, instead of learning so we've been learning the inference network, but instead of learning the generative model, you can specify it. So if you go into the problem and say, Actually, I know how to render bricks. I have OpenGL, I have a renderer sitting on the shelf somewhere. All I don't know how to do is look at an image and figure out the position of that brick. And you can use the same air network to do exactly this. So what we did was we took a rendering of a tabletop scene, and we said, okay, there's going to be some number of plates, some number of pots, and some number of cups, and there's going to be an unknown camera position. And given an image, what I want to estimate is all of those parameters. Where is the camera? How many objects are there? And where are they positioned in the scene? And to inspect whether it has done this successfully, we're going to take its representation, its inferred representation, and feed it into the renderer again to create a reconstruction. So it sees this image and it produces this reconstruction. And because they're identical, that tells us that it's inferred the camera exactly right, and it's inferred the contents of the scene exactly right as well. And for those of you who do computer vision, you'll recognize this as a very early idea in computer vision, like going back to the 50s and 60s, which people called inverse graphics. And the idea was that in order to solve the vision problem, we're going to have to learn to invert a graphics engine. I'll skip this as well. Now, I just want to make a shout out to a paper that came out like 2 weeks ago, I think, from Imperial, which is effectively doing something even more ambitious. What's happening here is you have an agent, so it's not just a generative model, it's an agent in the loop, and it's learning a neural network to look at an image and to produce a symbolic representation of that image, such that when you manipulate it with some symbolic front end, it allows you to take actions that give you good rewards. So in the loop of an RL agent, you're learning both perception and symbolic manipulation. And they show that this allows you to learn faster than you would with DQN-like algorithms that I showed earlier. Okay. So this is another paper that I worked on, and here, instead of trying to infer the objects, what we're trying to do is infer the mesh or the 3D structure that generated that scene. And again, for the same purposes of data efficiency. So I'm going to start off with the graphical model again as before. So we have these abstract codes, always the Zs, but instead of the Z directly creating the X, the image, what we assume is that the Z creates a 3D object first, perhaps a voxel grid that represents the object, or a mesh that represents the object. And that object gets rendered into the image. And what we hope to do is, given an image and perhaps some side information, to infer the underlying object. The reason why we think this is useful is because if I can go from Z to H, I can imagine, for example, what an object would look like from a different vantage point. Okay? And this is useful for manipulation. If I want to pick something up, it's useful for me to know what the object looks like behind what I can see. Or for intuitive physics, I know that if I drop this, I roughly know how it will bounce because I have an understanding of the 3D shape that it has. So again, we use big networks to do this, and we look at a bunch of different training schemes. I'm just going to point out one, which is to take an image as input and to use the old trick by now, which is of using an inference network to produce Z. This Z is then processed by a generative network that takes this abstract vector and turns it into a 3D representation. And then this 3D representation is passed through either a learned network or an OpenGL renderer to produce an image. And then by backpropagating through this whole thing, you learn the renderer, you learn the vector to 3D part, and you learn the inference network. And when you do this, you get results that look like this. So this first column are input images, and the second column are reconstructions. So the reconstructions are what the model is trying to do. The fact that they look similar is good. what we've imposed here is we've imposed the 3D representation to consist of a mesh of points. So what the network is doing is it's producing 3D coordinates for every vertex on this, say, 200-dimensional mesh. But what it allows us to do is now to take this inferred mesh and to rotate it. So it's looked at this thing, it's produced this reconstruction, but in its head, it knows it's a cube. And we know it's a cube because we can rotate it and we can see that it's a cube. Okay? And this is really only possible because we've built in the 3D rendering process into the system. Okay? And it's the same kind of thing. Convolutions build in some kind of information. The 3D renderer builds in another kind of information. And here we're demonstrating that you can exploit this information in some way. And another option, instead of using meshes as representations, is to use voxels as representations. And that's what is going on here. So first we train a 3D model of voxels. So it's exactly like the shape Boltzmann machine stuff on the horses, except on 3D stuff. And you can sample, for example, class-specific instances. So you can sample cars, or people, or plants. But more interestingly, you can condition on 2D observations and then produce a 3D mesh. So here, for example, we've conditioned on these views of this chair. In its head, it forms this voxel grid, and we can rotate that to inspect its kind of imagination of that object from different angles. And here it's completely learned end-to-end, and it knows 3D, basically. Okay. Another paper that made a huge splash recently is pixel recurrent neural nets. And this is focusing on the task of sampling good images. So they're building generative models, not necessarily with the aim of getting good representations, like what I've been discussing so far, but with simply the task of getting good samples. So everything that I've talked about has been these latent variable models, where the latent variables were the representations of interest. There's another class of generative model, the adversarial nets, which I'm not going to talk about. They don't necessarily come with inference networks at all, and they can only sample interesting observations. And the third are fully visible networks like NAID and a bunch of others. And pixel RNN falls into the third category. So it learns a generative model without ever building a latent variable. And it does this by exploiting the chain rule to the max. And I heard some of you learned about the chain rule yesterday, so this is going to be fun. What it does is it says, if I have an image, and it consists of a bunch of pixels, I can model the joint density on the entire image by applying the chain rule successively, where I say that the whole density is given by a bunch of multiplications, where at each point I consider the probability over xi, given all the pixels before xi. So the probability of xi depends on everything in blue, basically. And each one of these probability density functions I'm going to parameterize as a massive deep network, and I'm going to learn those parameters. You can see there's a recurring theme here. So the way they implement this is with convolutions. I'll explain in a second how this works. But basically, you have to really be careful about masking both in space and across color channels. So for this pixel, you're not allowed to look at the pixel itself to condition on, but you're allowed to condition on everything that came before it. But also in the color channels, for the red color channel for that pixel, you're not allowed to look at the pixel itself. But for green, you're allowed to look at red, and for blue, you're allowed to look at green and red. Okay, so it's really kind of conditioning on absolutely as much as possible without breaking the chain rule. And the way these are actually implemented in practice is by having many levels of convolutions, where the hidden state for a particular pixel is conditioned on the blue guy's hidden states in the layer below. And you just repeat this multiple times to get this kind of structure, where at the first level, you're only conditioning on, say, 4 pixels. But the second guy up here is conditioning on a much larger set. And if you continue this top guy is conditioning on a much, much larger set. And by applying this many, many levels deep, you condition on all the right things and nothing more. Yeah, I'm just going to skip this. And if you train this, what you end up with is a massive network, and you can sample from this network. And these images are samples generated by a pixel RNN that was trained on ImageNet. So it's trained on relatively large images of stuff. And this is the model's hallucinations of what plausible images look like, basically. And it's much higher fidelity than anything that we've been able to produce previously. So the reason why people keep pushing this line of research is because they think that eventually, we'll be able to train these networks on, all of Google images. And if they can produce images that look plausible to us, then surely somewhere in that network is everything we need to know about vision, right? Surely objects and structure and color and lighting and all of that is going to be there somewhere, and we just need to decipher it. So it's a very different approach to learning to the one that I've been working on myself, which is very typically quite structured. This is very unstructured. In terms of numbers, they just kind of beat everyone on MNIST. They get state-of-the-art. CFAR, they get state-of-the-art. You can. This is an interesting slide, actually. This shows why it's important to be probabilistic when training these systems. So what's happening here is you have an image, you're conditioning on half of the image, and you're trying to produce the black part. And every one of these images is a different sample from the network. So it's a different plausible explanation. And the 2 points are that, first of all, the samples look good, so they're not crazy. And the second is that they are variable. So it's not just producing the same thing over and over again. And I think the final column is the actual original sample. This dog one, I think, is quite cute. So it puts legs in all sorts of positions, and they all look kind of good when you look at the real image. So it's almost there, right? It almost knows what a dog is, but just not quite. Yeah.
Was the last column the train then?
Hopefully not, no. Yeah. Yeah. And you can do class conditional samples. So you can say, draw me an elephant. It draws you this stuff. Draw me a coral reef scene. Draw me a horse. Another way of looking at deep learning and being shocked is kind of just how far we've come. So remember the black and white images that I made in 2011? This is what we're making now, which is arguably a lot more impressive. Yeah, these whale ones are just incredible. These are generated by a computer. Okay, so the last paper I want to talk about is kind of a slightly more sober look at all of this deep learning stuff, and to mention that there are lots and lots of fundamental problems in machine learning that have existed for a long time and are worth looking at for a long time as well. And one of them is one-shot learning. This is kind of looking at the problem of learning quickly from a few examples and taking it very seriously, but interestingly also coming up with a deep learning solution for it. So in all of the networks that I've shown so far, the assumption has been that you take one thing as input, one image as input, and you produce one answer as an output. The interesting take that they have in this paper is they consider a scenario where you have an entire training set as input to the network, you have a question also as input to the network, and you produce one answer. So you have x1, x2, x3. Imagine these are your training examples. They come associated with them y1, y2, y3, which are their labels. And you have a query image. And what you want to do is you want to produce the label for this query image at test time. So for example, I can show you a small number of images, and I can give them names. I say this is a cat, this is a dog, this is a dolphin. I show you a new image of a cat, and what I want you to produce is this is cat. So this is kind of looking at that data efficiency argument in a completely different way. And the network that they design is so simple yet so powerful. So they take each one of the images, they form a low-dimensional representation, Z, for each one of the images. And then the query representation, they take the cosine of that, cosine distance of this guy with the representations for every image in the training set. And this gives you the attention maps. So A1, A2, A3, these are scalars. They're a single number that says how close is Q to X1 visually. And this is between 0 and 1, basically. And then all the network does is the answer that it produces is the weighted sum of the Y's weighted by the A's. So it says if I look a lot like a cat, then I'm probably a cat. And you can think of this as a neural implementation of nearest neighbors classification. Again, you just have a deep network, you have a bunch of inputs, you have one output, you differentiate, and then you pass gradients through the whole thing, and then you make it super deep, and it works. And what's interesting is that this subpart of the network is effectively, you can think of it as something similar to an ImageNet classifier. It's detecting whether the pair of images belong to the same class or not, effectively. And you can make this a little bit fancier by considering the scenario where the representations for each one of the training images you consider to be a function of all of the other images. So for example, if I'm looking at a bunch of images that are all of dogs, I might want to represent each dog slightly differently compared to when I'm looking at a training set that are half dogs and half cats. So the representation for every image is not just a function of the image itself, but everything else that's coming with it. And you can encode this by using, say, a recurrent net, a bidirectional LSTM to do this. So it's actually very simple to do. And you can even take it one step further and say that the question itself is also only going to be encoded after I've considered what my training data was. Yeah. And they tried this for one-shot classification and few-shot classification on a data set of omnicloud digits, and they get state-of-the-art across the board. So this is, like I said, just an example of taking a fundamental machine learning problem and kind of treating it a bit more seriously. And that's basically it. So to recap, we talked about machine learning, we talked about deep learning. Reinforcement learning is a way to allow our systems to generate their own data to do deep learning. And in my view, something like model-based methods are going to be necessary for us to scale these things even further, because we can't rely on our agents and only their experiences of rewards to train the networks. It's just not going to be feasible. So I guess we'll take questions.